Okay, so we are going to today's last lecture. I'm going to do two examples on buckling. I've uploaded this example on Avenue to Learn. Okay, my bad. I'm less prepared today than any other days. Okay. The exam, you have two questions. Both questions will be from your homework with a twist. As you already know, what is the twist? Okay, I might change the direction of the load. I might add a load, but you have seen the structure before. Okay, so do your homework, you'll be fine. It's going to be very similar like term test 2. Okay, let's put it this way. Okay, I will provide the formula sheet. I'll post a formula sheet probably this week by Friday. Okay. So let's look at this example, a very interesting learning example. A column of length L and a rectangular cross section has a fixed end B. So point B is fixed, okay, and supports a centric load at point A. Okay, so the word to take note is supporting a centric load. So for this course, I only teach you centric loading. I did not teach you eccentric. Two smooth and rounded fixed plate restrain NA from moving in one of the vertical planes of symmetry of the column, but allow it to move in the other plane. So at point A, right, there's a structure to restrict motion, and we'll talk more about this structure. Question asked is determine the ratio A over B of the two sides of the cross section corresponding to the most efficient design against buckling. B, design the most effective cross section of the column knowing that length L is equal to 20 inch. E is 10.1 and the load is 5 kips or kilopounds of load, and a safety factor of 2.5. Okay, so we're asked to design the most optimum cross section. Okay, right. So let's look at this structure is able to buckle on two planes basically. Okay, but what we are trying to do over here is to ensure both planes of buckling, right, are optimized, i.e., the structure will buckle in both the XY plane or the ZX plane. Okay, I know it does not sound that clear, but let me elaborate. Okay, because when I speak to you, when I hear myself, it's like, what is this? Not that clear. Okay, so let's look at this. Okay. Right. So this is our structure. So our structure has, we are going to look at XY plane. Okay, we're going to draw this on XY plane first. Okay, so we're going to view on XY plane. So XY plane, this is our Y. I'm following the transformation that's given by the book. This is X. Okay, so I'm going to draw that view. So when we sketch that view, what do we see? We see this. Okay, you see this. Then one end is fixed. So the other end you have at point. So this is our point B. This is our point A. Okay. So let me draw point A a bit offset because we have a load. So we understand that we have a load over here, which is P in the X direction, right? And then we have, okay, so this is the structure over here. Okay. Okay. So we are also so if we were to draw, this is our rotation in the Z, right? So at the end over there, or on the top, it is pinned. It's pinned. We allow motion up and down. So if we in terms of displacement, y will not be equal to 0, right? So i.e. it can move up and down at point A, okay? But x is equal to 0. We don't allow it to go left and right. Okay? We don't allow it to go left and right at all. However, moment, we also, in terms of moment in Z, okay, is not equal to 0, right? We allowed it to, yes. Yeah, you're right. Bloody hell. Thank you. You get another pint from me. He's right. Okay, I'm so used to. So y over here is equal to 0. X is not equal to 0. What's your name? How many pints I owe you now? Okay, so those of you I owe you beer, can you come to my office from today until the exam, 11:30 onwards? Come to my office to collect the beer. I'm serious, okay? Why 11:30? Because I have to go to the beer store, okay? I'm serious, okay? I'm going to buy about 30 cans of beer, so come and claim them, okay? Those of you online also. I cannot beam the alcohol online, but please come and collect physically. Okay, thank you, okay? So again, but the moment in Z is still correct, okay? Moment in Z. So this is spin. Whereas at point B, it is fixed. Y is fixed because it cannot move in X and Y is equal to 0. And moment in Z, right? Sorry, this moment in Z is equal to 0. What am I doing today? There is no resistance. Or moment in Z is equal, yeah, it can bend. Whereas over here, moment in Z is not equal to 0. Okay? So how this structure is able to deform is this structure can rotate this way. So I'm going to draw the deformation pattern now. Okay. So the structure is able to deform this way. Okay. Right. So that's where we know, okay, that the rotation, right? If you look at the rotation, the curvature is the same as RZ, yes or no? If you look at the curvature, it's the same as RZ. So when that's the case, we need to find, for this case, we need to find IZZ. Right? Remember I'm trying to relate this to remember have stress due to bending, right? Where we have y, we divide by IYY, Z, remember? Or plus or minus mz over IZZ multiplied by y, right? So when the moment is in y, we divide by IYY. When moment is z, we divide by IZZ, right? So mz, if we look at my, is the moment about y. So if you look at the deformation, the smiling face or the sad face is about the y-axis, right? Likewise, the smiling face or sad face is about the z-axis. So let me draw a transformation to elaborate this. So this is our x, this is our y, and this is our z. if the moment is in the y direction, you take IYY. If the moment is in the z direction, right, you take IZZ. For this case, and we know if the moment is about that direction, the deformation is also in that direction. Okay. So if we look over here, because of the deformation is the radius of curvature is the same as the RZ, we have to take IZZ. Okay. So for this case, we know that one end is fixed, one end is pinned. Okay. So the length over here, LE, the equivalent length over here is equal to 0.7 L. Okay. So how do we get 0.7 L if we look at the lecture last week? So one end is pinned, the other end is fixed. If you look at last week's lecture, right? We have a tape we have seen. So one end is pinned. So this is both ends. So one end is, where is it? One end is pinned, one end is fixed. Where is it? This is both ends are fixed. One end is pinned, one end is fixed. So we have this configuration over here, right? LE is equal to 0.7 L. In the exam, I will provide you with all these diagrams, okay? You don't need to memorize all this. I will provide you this diagram, okay? Right, then now let's go back to, okay? So now that is in the XY plane, okay? Then if we were to look this at this structure at a different plane, okay? Now we look at a different plane. Now I will look at the structure. We are going to look at the structure now. We are going to look at it in the ZX plane. So now this is our Z. And this is our X. So we are going to build this on X, Z plane. Now, when we view on the XZ plane, right? So now this is still our structure. The structure will be wider now. Okay. I think I make it too wide, right? Now the restricting, I'm going to sketch the restricting structure. Okay, so over here, I'm going to sketch in a different color now, right? Is it different color? No, it's not. You did. Come on. So now over here, this is the restricting structure, right? Basically, is the same thing that I've drawn for this. I'll just hatch them so you know what we're looking at. Now the restriction at point A, right, will not really restrict the structure at all. Let me elaborate what I mean. Okay. So over here you have X and Z, right, is not equal to 0. i.e., they can move in the X and Z direction, right? So now if I were to look at our rotation Y, right? And we know that moment in Y, right, is equal to 0. There's no restriction in your moment at all. So we understand that now at point B is still the same. At point B is still fixed, right? X and Y is equal, no, not X and Y, Z and X or X and Z is equal to 0. Moment about Y is not equal to 0. It's restricting. Okay? So how this structure will deform due to buckling is not the same as in as in the plate. Okay, so how this structure would deform? So we still see the load over here. This is our Tx. So now our structure will deform or buckle, not deform, this way. Okay. So for that's the case, we have one end, basically the other end is known as free end. Okay, it's allowed to do anything. Okay, so when that's the case, right, we know that our LE is equal to 2L. Okay, so where do we get 2L from? Okay, so if we look at last week's lecture, right, where we have one end is fixed, one end is free, is equal to 2L. Okay, is equal to 2L. So we go back